Hi, my name is Eric Torkia. I'm the Executive Partner and Analytics Practice Lead at Technology Partners Limited. Today, we are going to cover rank order correlation versus copulas, when to use them, what they are. The objective is to get this out of the way so we can do our next series to compare how the various packages, correlate variables amongst each other. So we wanted to get this theory out of the way. The packages we're going to use to do the demonstration are Oracle Crystal Ball and Vose ModelRisk. We could have used @risk or Solver, but in this particular instance we've picked these two. Oracle Crystal Ball, Solver, and @risk use rank order correlation, whereas Vose ModelRisk is quite unique in its use of copulas. So if you have any questions, please drop us a line at etorkia@technologypartners.com. So that's technologypartners.com. Welcome back. This is our series on understanding copulas versus rank order correlation. So what we're going to do is we're going to cover the theory of both rank order correlation and modeling copulas and see how they relate to each other. And if you guys need to know more or want to have a discussion internally on which method suits you best for your risk analysis, hopefully this document will help out in that process. So the first step is to define what are correlations. Well, correlation is a measure of association between two variables. If we're working with Spearman or Pearson's correlation coefficients, it's between -1 and +1 to indicate, the strength and direction of the relationship. So if it's a positive relationship, they both move in the same direction, and if it's a negative relationship, they go in separate directions. Monte-Carlo is really important, and if you don't do it, it could really skew the results of the model. And if you have to think about it and try to calculate it empirically or get some sort of expert assessment. Initially, linear correlation is something that most of us are familiar with. It's this least squares method line that we have over here. And in this data set, this line, it tends to approximate with this function and this r² value a fit that accounts for, according to this, about 70% of the variability or the linkages, and if we were to believe what we read, 30% of the movement or of this, the relative relationship is unaccounted for. And here we used a polynomial, so to think that it would try and fit better, again with the least squares method, and we came with an r² of 0.7827. If we wanted to translate these r² values into the Spearman, into Pearson's correlation coefficient between -1 and +1, we would do a square root of these values. Something to note when we're looking at correlating is that you can correlate the data points themselves, which here you can see that there are outliers, or you can look at log returns. And this was because we were looking at market data, and we could see that those seem to be more correlated than these crazy things over here. So rank correlations is a traditional method used to measure and implement correlation. The correlation is calculated between the ranks, rather than the values themselves. So if you had two columns of data, each column would be ranked onto itself, and then you would correlate using the Correl function those rankings. So that's how you would do Spearman's rank order correlation, which is the empirical way of calculating this stuff for, Risk Solver, Crystal Ball, and Palisades @risk. Now, one of the things we've been hearing a lot about are copulas, which is in fact why we're here. And copulas are basically a form of dynamic correlation. If you're going to do multivariate distributions, the basis for those are copulas. You can use it for nonlinear correlation, as you can see over here, for example. joint distribution modeling. And one thing to bear in mind about a copula is that it's a modeling tool. So this will enable you to apply flexibility in building your correlation pattern, but it is not an assessment tool like Spearman's Rho or Kendall's Tau. Different areas where copulas have done very well for themselves. Well, finance and insurance modeling. That has been at least what we hear of most. But if we look at some of the historical literature around copulas, a lot of it has to do around epidemiology, biology. More recently, we're seeing applications in oil and gas. And some of the places where I feel that it would be useful to maybe consider modeling with copulas are high uncertainty project risk analysis, so large where you have lots of data to work with. PMOs and projects have a lot of those types of relationships which are worth studying within an organization. R&D and software engineering, which is also has a high both R&D and software engineering have a high degree of uncertainty, and some relationships if you can get the historical data. So modeling with copulas. Well, copulas enable you to correlate on probabilities. You can inverse map probabilities to correlate losses, so this is really useful in the insurance industry. You can specify where the correlation happens in a probability range, so we'll look at that in a second. And conditional distributions are easy to express, and as we've seen with ModelRisk, simulation is readily available. So some of the things, more specifically, if we were to dig in some of those previous points, if you take into account that correlation is stronger for larger events, this is something you can deal with copulas. Quantifying correlation within a distribution, so the degree of it and which part of the distribution. So that's again something kind of nifty you can do with copulas. You can build conditional distributions over here. And this is an interesting thing. So a conditional specification gives a copula, and a copula gives a conditional. So what you could kind of infer is these are equivalent. And one of the last things is that you have basic copula families, and they're there because if you had to sit down and think through how to build out a copula, it would be really tedious and painful. So that's why we have these various archetypes to work with. Another thing that you can do is building multivariate distributions, and this is kind of an important feature of copulas. Usually the distribution of a sum of random variables is needed. Okay, so that's a good start. When distributions are correlated, getting the sum requires the calculation of the entire joint probability. So that's what we're here for. Here's an example of a function that might do, so a function of x, y, and z. So here you have the probabilities. As we said, copulas are useful for this, and you can get it for an all-inclusive view. Here's an example from a financial perspective of what a copula might look like, and I really do like the idea of it pulling the marginal distributions to join out to produce what we have is a joint distribution. So here's a visual representation, and we got this from Clemens and Riley, which were basically citing the relationship. So they were building a joint distribution between the FTSE All-World Tech Index and the FTSE All-World Specialist Index to see what would happen. And so this is over here is the scatter plot of what would look that joint distribution, and here are the histograms relating to the marginal ones. Within ModelRisk, if we were to look at this, because it's a nice convenient way of showing this off, here we looked at a bivariate Frank copula, and we devised our own little exercise. So imagine you have a class of 9-year-olds, and you want to correlate weight to height. So what we have here is that on the first variable, we took height, so 150 centimeters, with a standard deviation of 10. and then the weight was 120 pounds, not kilos, and again with a standard deviation of 10. And this over here are the joint probabilities of that distribution, if you like, which is a copula model. We're going to look at this. So here are the actual values. We can look at it from the percentile perspective. So the first percentile. And here we can see that there's a pinch when we look at the percentile view. So there's a much higher degree of correlation earlier on than there is in the earlier percentiles than we have when we take on the full. So this is, and of course this is not the same thing as what we were looking before. So here we're looking at a bivariate Clayton distribution, again for the same problem with the same distributions. One thing that's worth noting, and this is a very important thing, is that as we mentioned, to be able to model a copula, you must have some sort of sense of what the degree of dispersion is between the points. And to do this, Vose has included a conversion tool which enables us to infer more or less, and there's an uncertainty function in this, so this hops around as you generate the numbers, but it tells us what is the general correlation, if we were to compare to rank, with Spearman. So that tells us that sometimes we actually still have to correlate using, fit a correlation using Spearman to come up with this number. However, there is an empirical fitting tool that will do this for you within ModelRisk. Now, one of the things that we're looking at a T copula, and it's a bivariate, and really this goes a long way to explaining what is interesting about copulas, is that it will deal with what's in the tails. So very strong in the tails, and this is why you would do this, because you want to have granular modeling capability of this. So that's why in epidemiology and financial risk, in insurance and banking, this has been has been a boon, because this is where most of the stuff happens. Here are the different types of copulas. So we have a normal, Clayton, T, Gumbel, empirical, and Frank. So normal, we can see it's kind of pinched on both sides. Clayton looks a bit like a hose, when you're spraying in the summer your plants. A T copula is interesting for multivariate problems, though you could use it in a bivariate setting according to what we just saw. And over here, this is kind of like a pipe, so it's a very uniform type of correlation. This is empirical, so it takes the points as they are. And then we have a Gumbel, which is pinched on both ends, but much more tightly correlated towards the end. A lot of this stuff you can find on the internet. I'll provide some references in the article. And if you ever download a copy of ModelRisk, a lot of these things are covered as well. So conclusions. Copulas allow correlation of different parts of a distribution. The tail function help describe and fit as we mentioned earlier. And if you're working with a multivariate distribution, T copula is convenient, though it's not the only copula you could use for that. So if you have any other questions, please give us a call or send us a note at etorkia@technologypartners.com. That's etorkia@technologypartners.com. Thank you very much.